what is a good use case for a quantum computer. But first, let me say a couple of words about the company I work for. So my name is Michael Marthaler, and I'm CEO of HQS. And our company was founded in 2017. So me and the co-founders before that worked all at the KIT. That's an institute. That's a university in Karlsruhe. And then we started to work with companies like Bosch or BASF in chemistry. So with the goal of seeing how chemistry use cases would fit onto the quantum computer. By now, we also deliver software, so far mostly to the academic sector. And today, we still work on the question of identifying use cases for quantum computers. And we have a specific use case we work a lot on, and that is spectroscopy. And I will talk about this more in a second. But let me now talk a little bit more about this point about working on use cases. So generally, when we work on a use case, we go through 4 points. First, we say, okay, you have to identify a problem that somebody has. And I mean, it says here, identify industry problem, but that's of course important. But fundamentally, it should be a problem that somebody really wants to solve. In contrast, maybe to more mathematically abstract issues where the quantum computer has already shown quantum supremacy. So you might know that for the quantum computer, there are this type of algorithms that are really interesting on a fundamental level, but just have been created to show the advantage of the quantum computer itself. And so, of course, we want something where the result interests somebody. Then there comes a step called transform to quantum, and of course, then a step where you really want to benchmark against the best classical software. And at the end, you want to make sure that the algorithm or the issue you look at has a really good chance of achieving a quantum advantage. And now I want to emphasize these 2 points, and I'm going to discuss them also later more. The question of how you really get your problem into the shape that you need to put it on the quantum computer is one that is often a little bit neglected. And the need to have really good classical benchmark software. Since, of course, if people work on quantum computing, it's often already a lot of work, and then also to work on the best classical software is just sometimes challenging. But it's, of course, very important because if you have the best classical software, then at least you have really good classical software that works on a normal computer. That's also a kind of a really valuable thing to have. Now, of course, in practice, it's not that you go through like these 4 steps, but in fact, you look at the problem already a little bit and ask yourself, why would I believe that this should run on a quantum computer, or why should the quantum computer give an advantage here? So in some sense, you also go the other way around. Yeah, you look a little bit fundamentally, mathematically, what are the type of problems that, or what is the mathematical structure of problems for which we would assume a quantum advantage? And then you look around, basically, what are the problems that people have that could kind of fit to that? And so in practice, this goes a little bit back and forth, yeah, when you look at it. And actually, a reason I talk about this is because this whole procedure and finding really good problems isn't that easy, actually. So, I mean, there are a lot of algorithms, but if you go, for example, to like a collection of these algorithms, you can check out the quantum algorithm zoo. And then you do the following. You basically get rid of all the algorithms that have only a quadratic speedup. I cite here a paper down there here, where you want to read up why that makes sense to basically ignore algorithms that only have quadratic speedup. Then you take only algorithms that have a provable speedup, so no heuristics. Then you remove all oracles, all algorithms that have a so-called oracle that needs quantum memory. And you remove all algorithms only relevant for cryptography. I mean, cryptography is an important topic for quantum computers, no doubt. But let's say that's not what you want to do. Yeah. Then you remove all of them. And then actually the number of algorithms that remain is extremely small. And so the base algorithms aren't actually that many, and you really want to funnel as much into this as possible. And this actually turns out to be not that easy. So with that said, I want to discuss a couple of, here's the agenda for the rest of the talk. So first, I want to discuss some examples from our use case, from general use case research that are very popular, namely optimization. And I want to discuss shortly some recent work on optimization with provable exponential speedup. And then I want to comment on heuristic optimization with algorithms like QA/OA. And then at the end, then after that, I want to go through a full use case example where we put a lot of work in at HQS. All right, let's get started with the optimization. Now, generally, a lot of people who work on quantum computing work on optimization. I guess most people know what that means. Yeah, combinatorial optimization is a very common mathematical problem, and appears basically everywhere. So fundamentally, everybody already agrees, okay, if you can solve optimization, it's gonna be valuable. Yeah, so people don't necessarily need to show that much in detail. It's generally believed. Now, however, until very recently, there was no provable speedup, I would say, or no provable speedup beyond quadratic, let's say, yeah, available. But very recently, people have shown a provable speedup for, unfortunately, a highly specific optimization problem, namely the optimal polynomial intersection problem. So to be honest, I have never heard of this problem either. Yeah, so I don't think anybody here had heard about it. What that means, it's a problem where you have a polynomial function, as shown here, for example, in this blue line, and you have areas like shown with this orange spaces, indicated here as fi, and you want your polynomial function to intersect as many of these areas as possible. So you optimize for that. I took this picture actually from this paper here, from this archive paper here. It's called Optimization by Decoded Quantum Interferometry. So it's very nice that this picture explains what the problem is, because otherwise I could not have understood it. But nonetheless, what they show in this paper is that their algorithm solves this problem, or solves a so-called achieves approximation ratio in polynomial time faster than any other algorithm. And is there a question? Okay, I was just wondering. If there's a question, don't hesitate to ask. And therefore, in principle, this is a pretty strong progress. However, this would be one of the cases where you would really need to work on the transform to quantum step. I mean, how do you get a real optimization problem? onto this kind of relatively uncommon optimal polynomial intersection problem. Nonetheless, people are working on it, and I think it's a quite interesting direction. So at very least, you have a provable speed up for this optimization. Yeah, I mean, here I show it actually. So yes, so you really need to work on this question of how to get your problem to this polynomial intersection problem. And of course, you know, if you really take your original problem and solve it with the best code available, will this speed up remain is to be seen. So it's also very important to have the best code, the classical way available for comparison. All right, and now a comment on heuristic optimization. Here I actually have also a slide on a general optimization problem. So if people don't know what that is, but let me just say, I show you some equations. Generally, often the idea that the quantum computer should help on optimization is motivated by an algorithm called the Grover algorithm, where you somehow start in an initial state that is the state of all possible kind of solutions. That's very trivial to generate. And then you act on your state with some type of operations that generate a phase, and somehow you hope by interference or whatever that only the ideal solution remains. Basically, in Grover, you have a provable condition that this happens, but in all these heuristic ideas on how to do this, you somehow hope that this also works. And we can look at basically, and now what we can do is give us a little bit of a feeling if that actually makes sense by looking at the provable Grover algorithm and ask us what this would help us for an actual optimization problem. So the optimization problem I show here is the traveling salesman problem. So for the traveling salesman, this is the problem where you say I have a certain amount of cities and I want to have the shortest path between these cities. So this is also the standard optimization problem that you normally people cite. And if you hear that the quantum computer is good for logistics, this is what this refers to, that the quantum computer is supposed to solve the traveling salesman problem. Now, if we were to solve it with the Grover algorithm, then this would mean the following. The scaling for this problem, classically, if I have n cities, so I have n cities, and what I do is I do a classical brute force search for the fastest path. Then I would need to search n faculty paths. So this is quite a lot and scales really terribly. However, on the quantum computer, this would be better. So if I would do Grover, this should be a square root n faculty. Yeah, so better, but still actually scales terrible. And I write this Grover question mark because actually I'm not aware of a paper that really shows end-to-end how to use the Grover algorithm for the traveling salesman problem. So and it turns out that the best classical algorithm also scales better than n faculty. It still scales exponential n squared 2 to the n, but better than square root n faculty. So in fact, the best classical algorithm would scale better than a brute force use of Grover on a quantum computer. Now it turns out that there is a quantum algorithm in this paper here, quantum speedups for exponential time dynamic programming algorithms. And so the best proven quantum algorithm scales like 1.728 to the power of n, at least this is what the paper says. I welcome you to look into this paper to see how complicated actually this algorithm is supposed to be. And I think there are a lot of steps that are pretty unclear to me in this proof. So I think it also remains open. However, back to the conclusion, given that already for the Grover algorithm, there are a lot of open questions, and for the Grover style approaches, there are a lot of open questions. I feel that heuristic approaches where we just try out something and hope somehow that an optimization problem gets solved have very little chance of working, and I would rather rely on proven approaches. And with this, I want to really come to the last point here in this optimization section of my talk. Generally, if you look at real problems, I would really first always work on the step of thinking about getting the best classical solver and checking out kind of what you can do by really improving your classical solvers. And if you want to work on the quantum computer, it's really fine for the problem that you want to solve to be a little bit more abstract, like the polynomial intersection problem, and really checking, do I really have actually a speed up? Do I expect the quantum computer to really perform better than a classical computer? And with this, I come to an actually full use case example where we work on a lot at HKS, and this is nuclear magnetic resonance. And I think people here probably are not fully aware of nuclear magnetic resonance, so I want to explain to you what that is. Nuclear magnetic resonance is a technique in chemistry and pharmaceutical industry where you have a machine as shown in this picture here. And what you do is you have normally a vial full of some liquid, and in this liquid is a molecule. And then you irradiate this molecule with microwaves and get back some microwaves and measure that. And then you plot a spectrum, so kind of the frequencies of your microwaves that you come out. And this machine is so big because it has a big magnetic field, and this pulls all these frequencies apart such that you can distinguish them nicely, or more or less nicely. As you can see here, it's already pretty crowded down here, and only some of these peaks are well separated. And now what you can do is you actually know that this microwave field interacts with the nuclear spin of a hydrogen atom. So here's a hydrogen atom, and you know by the frequency of this peak here that some kind of other part of the molecule is attached to it. And this is normally tabulated. There are books or other tables where you can look this up. And then somehow you have another hydrogen and some other part of a molecule is attached to it. And now you have the difficult problem of looking at all these peaks, and somehow you have to figure out that what you see here, all these peaks, actually it turns out that this is the spectrum, the nuclear magnetic resonance spectrum of mentor. And okay, this technique existed 50 years, so people can do it. So you can put all of this together, but actually it is even today quite difficult. So what you want to do is, what you'd rather have than putting all this together is a simulation method where you put in the molecule and say, this is my molecule. And now what type of spectrum comes out? So then you can compare and say, okay, is this the spectrum that I've measured? Then I know that this is the molecule, and so on. And what I now want to do is, so this is a problem that exists very much in industry. And now I want to jump directly to this question of why this is a good problem for the quantum computer. Yeah? So why would this be a problem that attaches to the quantum computer? Fundamentally, it starts from the fact that what you see is basically an effect from spins. Yeah, so this is the microwave field that you see comes from the fact that you excite with your microwaves that you put in, you excite the nuclear spin. And as you might know, the nuclear spin is mathematically equivalent to a qubit. So there's a really one-to-one fitting between the problem you have, the kind of the motion of spins in the molecule, to kind of your qubits in your quantum computer. And you might have seen actually qubits being depicted with this type of sphere, where you have a sphere and an arrow depicting the state of a qubit. And actually this sphere was not, I mean, the first time when people wrote down this sphere, so this was Bloch, this is a Bloch sphere, it was done to describe effects in nuclear spins. So it was done for spin physics and only later adopted for describing things in qubits. So what you see is there's a really tight connection between the physics we describe in a qubit and the physics we have in a spin. And therefore, when we solve this type of problems, it's only a little bit more than actually just time evolving the spins of our quantum computer, or the qubits of our quantum computer. And here we do this, for example. So this was done in the cloud using an IonQ quantum computer for this small molecule shown there. So this is really this very small problem, only 2 spins. But you can do it directly in the cloud, so it's not a big problem. And now maybe to become a little bit more technical, the object that you need to calculate is kind of this time evolution between an initial state of your spins and then a time evolution of a Hamiltonian. And I will talk a little bit more how to get the Hamiltonian later. And then you measure your final state. And that's it. So just a spin time evolution, yeah? Which is the most obvious thing where the quantum computer can achieve quantum advantage. Now, actually, it gets actually even better than that in terms of quantum advantage probability, because you have here the sum over all initial and final states. And of course, you don't calculate this. You sample it. So actually, this is a sampling problem. And you might also know that sampling problems are also the most probable type of problem where the quantum computer has an advantage. And it turns out that actually, if you want to solve this exactly classically, this scales like 2 to the 2n on a classical computer, meaning if you have n spins, it scales like 2 to the 2n, not 2 to the n, meaning all ready for 30 spins, and there's no exact classical solution anymore. Yeah, so even classically, you have to become approximative, but that's often possible, by the way, and I talk about this too. You have to become approximative if you want to solve this problem. So it's the most ideal problem for the quantum computer imaginable. And of course, that's fundamentally interesting and also quite interesting for us to find good problems for the quantum computer. But of course, we are also quite interested to solve it just in any way possible. And with this, I now want to discuss and give you a bit of a feeling why this transform to quantum step is so important and what we do about it in practice. All right. So actually, the problem that we want to solve is a spin problem, and it's described by a Hamiltonian that looks like this, where we have here this spin degrees of freedom I as written normally in nuclear physics. And then you have 2 types of constants, the so-called chemical shift delta I, that is the reaction of your spin to an external magnetic field, and the spin-spin coupling, Jij. And these kind of constants you need before you can put this problem on the quantum computer. So you get your molecule, you need to then get these parameters, and then you can define the Hamiltonian, and then you can put this time evolution on the quantum computer. And these chemical shifts are basically these numbers that give you the feeling of how your nuclear spins couple to the rest of the molecule. And generally, this type of workflow has to look like this. First, you put in your structure exactly like I do here. So you tell your computer, and I give an idea how the molecule looks like in this 2D structure. But that's, of course, only a rough understanding of the molecule. It's more like your personal definition of how it looks like. And then you have to basically create a quick 3D structure and start to sample over all different conformers. It means, for example, this is rotating and oscillating and so on, and you have to sample over this until you get these parameters. Yeah, and this is, for example, how this first steps looks like. Here it's also shown a molecule put in this 2D structure or as a smile string. Smile strings are also unique ways to define the molecule. And then you get a rough initial structure. But if you would take only this initial structure and calculate a spectrum, it would actually be very far off from the experiment. Yeah? So there is a big difference. So you have to take these other steps and start to sample over all the different relevant structures. And then it becomes better. But actually, we also have this additional step of structure refinement. And this is a critical necessary step. And actually at HQS, the largest amount of manpower goes into this workflow to make this really good. Because this is a really critical step. If our calculation here is bad, everything that follows on the quantum computer also will not gain any, will not be of any advantage. Yeah, so this needs to be really good before we go to the quantum computer. And so this is basically a typical case of transform to quantum, where you first have to get the relevant parameters. And this has to be in really good shape before you go to the quantum computer. Here's a case where we show that we can achieve really good parameters and calculate really good spectra. So this is a simulated spectra versus experiment. And of course, these spectra have not been calculated on a quantum computer. This is also our classical solver. And with this, I now want to say, okay, let's now talk a little bit about this fact that you want to have the best classical benchmark software available. So here I show you a case that we had, or that we have, where we thought, oh, this is really cool. Maybe this could be a case where which we put at some point on the quantum computer, and the quantum computer will show a clear advantage. It's a molecule with 50 spins. And as you know, 50 spins is pretty hard classically. So this should be in the quantum advantage machine. And this is a measured spectrum. So the molecule is called Fridolin. And this at 80 megahertz gives you, actually is related to the magnetic field strength of the spectroscopy that was done. And here's the spectrum. So we have measured data, and if we could put it in the quantum computer, we could compare to the measured data and see, okay, this looks good. Now, actually, though, this can definitely not be solved exactly classically. But do you really need an exact classical solution? This is, again, a big picture of the molecule, and I show it also to show one of the things that we found really appealing of this molecule is that it's very rigid. So it's not oscillating or so. So calculating all the conformers and averaging over everything is not that difficult. So we could do it. But now, if you now think about solving this classically, instead of solving all this huge spin problem completely, what you can do is you can choose clusters, where you say, okay, these spins down here in this hydrogen don't need to know what's happening in this hydrogen up here. And these are clusterization methods, so this is pretty well understood. that fundamentally this type of problems can be, this type of methods can be found. And and we use this type of method to calculate it classically, and we adjusted a couple of parameters a little bit. So we shifted overall the spectrum a little bit. And then in the end, what we could show is that depending on the cluster size, our classical solution converges completely even at a cluster size of about 14. So 14 spins in one of these clusters is enough for our classical solution to converge. The comparison is sufficient. And therefore we see actually we can solve this problem still classically. So here it was pretty important to have a really good classical solver. It showed us that actually we can solve this problem classically. And it's also an advantage for us because we can still also show that we can solve huge problems classically. However, cases exist where actually this type of clusterization doesn't work. So this is a molecule from phosphor chemistry, a diphosphane molecule. And this type of phosphor chemistry is super important in biology. So in all type of biological molecules, phosphor appears. And their clusterization is not possible. So this phosphor couples all the remaining molecules, all the remaining spins very strongly to each other. So no clusterization is possible, and really big changes happen if you clusterize or not. So this is the clusterized spectrum, and this is the actual spectrum, and you see there's even a qualitative difference between them. And with this, I'm come to the end, and what I want to say is that we are actually publishing use cases for the quantum computer, and use cases means not just ideas of what to do, but we are publishing all these Hamiltonians for NMR. And actually, this has already been published. So if you want to have a look at this, you can check out our use case repository, which is public. And there's the link in this QR code. And of course, you can contact us or follow our YouTube channel, where we also kind of regularly publish videos on our use cases and our software and so on. Yeah, and with this, I'm at the end of my talk.
Thanks for the talks. So I'm open for the questions from this the audience here. Any questions here? Yeah, before that, I can ask a couple of questions. So even this NMR giving a very good background for the quantum computing for applications. Even I gave a talk last week. Because I'm not working NMR things, but I gave this. But what about other applications? Are you really working for this on behalf of NMR? Because financially or logistics, something like that, your company doing some work?
Yeah. So things like logistics. I mean, people have started to take this work here with the provable algorithms and started to try to really get this transformed to quantum step for some real problems and transform it not to this polynomial intersection problem, but to min x or sat or whatever. It's also in this paper. So there are papers already where they try to really show how to get actual optimization problems that people really care about to this provable algorithm. But I'm not fully aware how well this is going. But people do it, and it sounds really interesting. It's a good direction to work at. So it's possible.
Good afternoon, good morning. Has anybody actually solved a problem in quantum computation? Or you're just formulating and working on the algorithms, efficiency and things like that? Has anybody solved a practical problem so far?
So far, fundamentally, in the whole world, I don't think anybody has solved a practical problem on the quantum computer.
Okay.
What has been done is this very abstract type of problems where people have shown quantum supremacy, but these are abstract sampling problems. And basically prototypical tests like this one. Yeah, but this is not I mean, could do this classically as well. This is not something where I need the quantum computer for. I'm just doing it to fundamentally show that it works. So this is the state of quantum computing.
What is the reason for this optimism, extreme optimism, which is going on right now all over the world? Is it justified? I mean, is there any? I mean, do we have a chance of, say, quantum computer, say, another 10 years or so?
10 years, I'd be optimistic. But in the very near term, like in the next 3 years or so, I would say I am hopeful that we get some niche cases running in something that's practical but pretty niche running even in the next 3 or 4 years. But beyond that, like a broad application, I don't see at least in the next couple of years. Yeah.
Okay, thank you.
Any other questions? No questions from?
Huh?
Please.
So 2D NMR quantum, is it possible?
Sorry, again?
2D NMR?
I didn't quite understand, sorry.
The two-dimensional NMR.
Sure, of course. Yes, two-dimensional NMR is possible. Yes. There's no fundamental problem. Anything you can do in NMR, you can do on a quantum computer and simulate it.
Okay, so what is how the signals are sensed, sir, using quantum computing? See,
I mean,
is it diamond used, or what kind of material used?
I mean, so for the quantum computer,
Yes.
it depends. Yeah, for the quantum computer, I mean, you use, I don't know, whatever material. I mean, you can do a diamond, or you can use normally the quantum computers we like to use are superconducting. But it's not one-to-one. I mean, you're not really having the same NMR on. I mean, since you can flexibly have your qubits interacting, yeah. I mean, it's a computer, so you can program it. You can say qubit 1 interact with qubit something, and so on and so on. I can put any molecule, map it to the quantum computer with a certain overhead. Yeah. So the material of the quantum computer is in some sense irrelevant for the NMR problem. But okay, so for your interest, the ones we use are superconducting normally. The one I'm showing here actually are trapped atoms trapped in a kind of a electrical or electromagnetic trap.
So the examples you had shown, maybe I missed it. Any proteins actually you had shown? Because I could see.
No, we are
much
not. I mean,
protein.
so
Yes.
yeah. So let me show you a couple of molecules. The type of molecule we are doing. Penicillin, for example. So we are doing artemisinin camphor. We are not. So we could do protein spectroscopy if we fundamentally from our software tooling and so on.
Yeah.
But we generally and we could also fit it on the quantum computer, but we don't do it generally. Since the feedback we got from people was generally that small molecule NMR is more, let's say, the bigger topic. But we are of course open if people are interested in protein NMR. We are open.
Oh. Thank you, Dr. Michael.
Any other questions? Okay, Michael, I have one curious question, but maybe don't a silly question. Okay, so you started in 2017, like means almost 9 years, almost 8 years working in your company. So you said that the quantum simulators, for example, there are many simulators, IBM, there are many devices. So if the NMR problem due to the simulator, you give some results like 1.78 something V6 power n, you put some answer. So same thing, I will get the result from the real-time quantum. Like if you go to the ion trap or if you go for superconductor, if you go any real-time quantum computer, the same result will come or some near result will come. Any guess?
I didn't fully understand the question. Can you just repeat?
See the people working in quantum simulators. For example, simulators give a simulator, give us some results. Okay. For example, any for IBM or you have a own simulator also. Okay.
Yeah.
So if you go to real-time quantum computing, real-time, because I'm saying that you can go to superconductor device or ion trap, whatever in future.
Yeah.
Okay. Same problem I can do to this problem to the real-time computer.
Yeah.
I can get the same results. Maybe the result from this simulator is like 1.78, some approximate results from this simulator. Can I get the same results? Like guessing.
So you're asking if basically if I currently simulate the quantum computer and ask myself if I can get the same result on an actual quantum computer. Yeah. So currently the problem with using the actual quantum computer is that they are very noisy. So they have this problem that they are performing in a pretty unstable fashion. And therefore, this limits currently massively what you can really do on a quantum computer. So you could, for example, this algorithm down here, the one with the proven speedup, you could definitely not run right now on an actual quantum computer. Inconceivable. Just look into the paper; it's just unimaginable. And that, of course, limits also a lot what you could do, because heuristic optimization, where you just try out, could be powerful in principle, but you would really need a very reliable and easy to use way to constantly test it. And you can't. You have to know in advance what you do really, really, really well. Every little piece has to be optimized. When we run this type of experiments here, every gate we run has been optimized down to the absolute optimum, by hand to make this work right now. And any other way, it's just not really possible to do it. Fun fact, look at the high-end papers from anyone, from IBM, from Google, from anyone. All they run is basically spin problems.
Yes.
It's basically always abstract spin problems, and at very least, they have a real spin problem here. Not an abstract one, it's a real one. So this is currently what's working. It's what's going to work for a couple of years. And then we'll see. Yeah. And I think for this long-term work, it's more important to work on this more abstract question of how do algorithms scale, so on this provable question, than to try out too much stuff.
They're more challenging in future. Let's see. I think I hope there's no more questions. I thank the speaker today, Michael, because very early morning. Thanks, Michael.
Thanks.
Nice to meet you next time in future.
Thanks.
Thanks. Have a nice day. Bye-bye.